I'll come after class.
Yeah, after class you can do the start issue. I don't think class will take too long today.
How's the midterms?
I sent them.
Yeah, I saw the results.
Uh-huh.
Like, how's 75% all like?
So there is the standard deviation and the average also connected to that. So you can think about that if it's curved. Right? Since it's better than average, you're at least going to get something like a B for the midterm. If you did above the standard deviation, then you're probably getting an A, right?
Alright, awesome.
Yeah.
Okay. Awesome.
How come I'm not getting any? Oh, okay. There it goes. There it is. Yes.
The flow is like that. I'll cover the first part, the context of constituency parsing, and then usually I'll cover
Okay.
so usually that some introductory slides.
Okay. Do you want to give those? Give me the link or put it on the Slack on your prep chat channel. Then I'll manufacture yet another link. Hi.
So, do you will you have time somewhere in the evening, like by Skype, so that I can send you the topics and
Yeah. I'll be around. I don't think I'm going to sleep tonight again, so I will be in school.
So maybe, oh, you will be in school. So should I stay then?
Yeah.
I don't have my
going to eat
laptop
dinner.
charger. Otherwise,
Oh,
but I can connect via Skype. Via Skype.
okay.
So I will create the slides on what the things are, and I will talk to you via Skype at what
Okay.
time.
Sure. Yeah. If you need a charger, I have plenty of
Oh, then it's
chargers.
fine. I can take the charger. I can stay. That's
Okay.
not a problem.
Yeah. So I don't have it with me right now,
Oh,
but
okay.
because this one drains battery very fast.
Yeah, exactly. Mine is also now it just.
Okay. So if you need to go, then you can go. Otherwise, you can.
No,
come.
actually, I was running experiment. That's why I need to go. I still need to do something.
Okay.
There's like the main point is that after clustering the first level topics, it's not sharp. The clusters are so fuzzy that you won't be getting like exact division, which is
Okay.
kind of trying to find the parameter.
Okay.
So
Maybe I'll try to talk to you after class because we're trying to get started.
right. So I will
Okay.
talk to them via Skype,
Mm.
and I'll send it. Okay. Thanks.
Okay. Thanks. Sorry about that. No. Yeah. Okay. And hope that works. You need permission from your slide deck. So you go to your slide deck and you just say share to everyone. Okay. This slides first. I already have this first slide deck. We'll just get the second one. Yeah. So wait for you.
Only one on the internet.
Yep. There it is. Okay. You can start whenever you're ready. So today we have perhaps a little faster class. We have only 2 presenters today, so unlike the earlier classes where we had a lot of people helping out, for some reason, even though I assigned a lot of people to the end of the semester because I knew that going to happen, we have fewer people to hold the fort, so to speak. So I hope it will be even more like a discussion group than a lecture. Okay, so I hope all of you will chime in. So we're going to have Stephanie present the first half, and Eugene will be presenting the second half. Okay? Yeah.
Hi everyone, I'm Stephanie. So, pardon me because I'm not too familiar with NLP in general. So I'm also very new to this topic. But firstly, I'd like to just go through a couple of slides with you on what actually is constituency parsing, because that is the topic on top of 3RNN, which Eugene will cover in greater detail. So there'll be just 3 parts I will talk about, which is what is constituent, what is a constituent, okay, and then there's this thing about context-free grammar, which is actually a model to model the language, and then constituency parsing in the context of using 3RNN to parse. So my question now is, think about this, how do words group together in English?
Actually, camera is on, but not the.
Should I start again?
It's up to you. You can continue where you are, or you can start over.
Okay, so yeah. So the thing before we understand about what is a constituent, so how do the words group together in English? So you can first consider a noun phrase, and then you think about what evidence do we have that these words actually group together. For example, Harry the horse, that's a noun phrase. The Broadway show, day, even day is also a noun phrase. So there are some evidences of grouping. For example, you see in the left-hand part of the slide, which shows 3 examples of groupings. For example, the 3 parties from Taiwan arrived. So arrive is a verb. The Broadway show represents. It's also a verb, and basic. Then from there we can know that there is a kind of grouping with the noun phrases, and that occurs before the verbs. And there's another kind of grouping, which is, you look at the second half of the slide. Yes, the structure is a little bit different. So on December 10th, I like to take Singapore Airlines from Singapore to Bangkok. The second line, I like to fly on December 10th from Singapore to Bangkok. And I like to fly from Singapore to Bangkok on December 10th. These are also different evidences of grouping, where there's a pre-post and a post-post construction. And from that, you discover that, oh, on December 10th is a grouping. So we try to discover the groupings through these pre-post or post-post constructions.
So just to interject here, we're talking about constituency grammar. So everyone are again remembering what we talked about constituency grammar. Right. Constituent means that you have a subsequence of words that are all contiguous, that have a semantic system. It's different from dependency parsing, which we also cover. Dependency parsing has all of the stuff in constituency, which again not go over with the idea that we have a union that's contiguous as a on the previous slide, which you were showing about constructions, we have prepositional constructions on the right side. And so a preposition in English is just a particle that comes before whatever clause it's governing. And then you stick it in various positions, as Stephanie was showing you. You have a type of prepositional adjunct, which are at the beginning, some in the middle, and some at the end. So both the noun phrases and the verb phrases are the types of constructions. Building them up recursively.
So, Prof already covered this part. Then mention something about context-free grammars, which is actually a formal system for modeling the constituent structure in English. And it is also known as the phrase structure grammars. So in this model CFG, it consists of rules of production, a set of rules or production, and that actually expresses the way the language can be grouped or ordered together. And more importantly, these rules can be hierarchically embedded, and we can also combine previous rules with others. So I'll show you some examples of recursion and ways of grouping. So a very simple one would be a rule embedding for past P for flight. So a flight is actually a noun phrase, but if you break it down, it's actually a determinant and a nominal. And also, A is the determinant, and actually this nominal is also referring to a noun, flight. And we have a more, slightly more longer sentence here. It's he eats spaghetti with a spoon. And you can see how the hierarchical embedding, the hierarchy is formed. So let's think about this. Are languages actually recursive?
I think Stephanie is asking you a rhetorical question.
Yes.
Are languages recursive or not? What do you mean by recursion? Let's go back to the previous slide when we were talking about phrase structure grammar. What is phrase structure grammar? As Stephanie says, there's a bunch of rules or production rules that are concerned with phrase structure, right? So let's go through what a grammar is and what a lexicon is. Are we all clear about what that is, or do you want me to talk about it contemporaneously? You guys are awfully quiet. Did you eat your dinner? Is that why? Did I just? Okay, let's start from the basics. What's a lexicon? Yeah, so dictionary, no, it's like a Python data structure, right? But it's actually modeled after the book that we used to actually physically have. We don't have too many of those anymore. So what's a dictionary, right? It's a lookup table, a hash table, right? And if we think of it as the thing on the shelf, which is also a hash table, but we look it up in the same way we find binary search on a dictionary, you have a key in some lexicographical order, and you have a value, which is a definition, right? In a grammar, when we produce language, what we want to do is look up a word and then find its parts of speech. Okay, what's a part of speech? What functional category a word is, right? So Stephanie just said flight is a type of noun. Flying is a type of verb. It's also a gerundive noun, right? So you can say, the flying was terrible, right? So that's a noun, right? So there are lots of words you look up in a dictionary, a lexicon, and they have different parts of speech, right? So who can give me a word that has multiple parts of speech? There are plenty of words that we know that have both noun and verb parts of speech. Come on, guys. I actually can say guys because all the guys are guys. There's only one female here.
Yeah, now he's empty. A word that's both can be considered both a noun or a verb.
Right. Home. Hope. Yeah. To hope or the hope. Home is also a verb. Home on something. Home is also a noun. My home. Right? Almost every verb you can think of is also a noun. To eat. To eat. Right? Jump. The high jump versus new jump. Okay. So these are all things that are in our lexicon. Okay, so that's one part of natural language when we're talking about parsing. The other half is the grammar. So what's the grammar? It's this stuff on the slide, right? So what's a grammar? They're rules, right? Eugene says they're rules. It's basically a listing of rules. What are the rules for? Right. Right? We use the rules to see whether we can construct the structure of the sentence given a string. Right? So I have a production of words. I'm trying to make sense of these words and give structure to them by applying recursively rules that come from this list of admissible English or admissible Chinese or admissible Vietnamese rules. Okay? And if I can apply those rules in some order and get out a structure, and that structure, when I linearize it, means discard the tree and just get out the final sequence of words, that is an admissible structure. And then it means the sentence is in the language. That's how we, syntactically as a linguist would think, what it means to be in the language and not in the language. So if you read all the linguistic literature, you see all these sentences that blah, 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 and then they put a star at the end. What does the star mean? It means it's not in the language. Somehow it feels awkward to say it like that. Okay, so like some Singlish sentences to an American speaker would be starred. Right? Like, you can't say it that way. Okay, but we say it that way anyway. Right? Okay, so when we talk about linguistic structure, we almost always think about these two parts of a language. One is the lexicon, meaning the hash table of words to parts of speech. They represent the last penultimate layer in this thing, right? You can see the penultimate layer is always a straight line from a part of speech to a word. Okay? That's your mapping. Okay, that's the lexicon. Okay? The rules is everything else. Right? All of the syntax, all of the production keys, all of the rules are everything else in the tree. All the non-terminals. Okay? So when we're thinking about this thing linguistically, it's like computationally, that's what we're doing. Okay? So you can see here there's some production rules that you can see. Alright, so for example, on the last layer here we have determiner. A is a type of determiner, right? That is in the lexicon or in the grammar? Lexicon. Okay, we have one person who's big enough to say lexicon. Okay. How about another rule? I can make a noun phrase from a determiner followed by a noun verb. Is that in the lexicon or in the grammar? Grammar, right? Do we all see that? Okay. All the funny-looking branching structures are not in the lexicon, right? They're all production rules that are in the grammar. So the way you can read it is, for example, sentence, like the S, the top S structure at the top of this right-hand side of the slide. A sentence can be rewritten as a noun phrase followed by a verb phrase. Right? I don't care what is in the noun phrase. I don't care what is in the verb phrase. Okay? I just know that a sentence can be constructed as these two constituents sitting next door to each other. Okay? And recursively
figure out what those things are. Because I have another production rule, right? It says a noun phrase can be rewritten as a pronoun, P-R-T-E. Okay? So I can just take that variable and replace it with another variable called a pronoun, right? And then I use the lexicon to say, hey, you know what? There's a type of pronoun when you lexicalize or you take the word he is a type of valid pronoun. Okay? Are we all following this part? Okay. So this is what we call a context-free grammar. And I think Stephanie is going to go through the Constituency hierarchy, right? A little bit?
So that was the primer.
Okay.
So Neon Chomsky, basically he's a linguist, so not from the computer science section, but it's very important that you know the linguistic method to compute and make sense of the sentence structure. So Chomsky thinks that recursion can be a natural way of describing language. Of course, this is cognitively debatable depending on the sentence structure and the rules that you come up with. But one example of a way of recursion could be the man from the canteen that you spoke about, the food yesterday. So you notice that the man from is probably the first part of a second of branching. It can be divided. So from the sentence, you can divide it into the man from and then the canteen that you spoke about with the food yesterday. So the canteen that you spoke about with the food yesterday, it doesn't really make sense. But, what was I trying to say? Yeah, so there is a timing at which the man spoke to you, which was yesterday, and you can again break it down into two parts, and then the canteen that you spoke about with about the food, that's another bracket over there. I did not put that. And then the food itself is also the noun food. I hope I got it.
Okay, so let's go over this phrase. The bracketing is wrong. So,
yeah, the bracketing is wrong.
What we're seeing here is that constituents have to be defined in a certain way. Okay, you cannot just put the brackets anywhere. So, for example, what is this entire sequence word? Is it a sentence? What do you think it is? The man from the canteen that we spoke with about food yesterday. It's a noun phrase, right? It's a noun phrase. So we can recognize that, but internally somehow you're parsing that and you know the structure of the sentence, right? So for example, from the canteen is a constituent, right? It makes sense. When we hear from the canteen, we can make sense of it as like something from the canteen. It's a prepositional phrase. So the brackets that Stephanie had on the slide is not correct, right? But many times when we hear construction that seems to be grammatically correct up to a certain point, we are internally building the structure of the sentence. You see, the canteen that we spoke about, well, the canteen that I ate chicken rice the other day is also an admissible noun structure. So you might be building that constituent in your head, but because it ends in a funny way, you have to go back and think, okay, is that correct? Right? So the bracketing is showing you that even though certain structures are admissible, when you generalize at the top level, sometimes those things that we are building in our head are not. Okay? There's a very, you can Google this, you can put in the term garden path sentences, okay? Which are sentences that people construct in linguistics for fun, just to show that these types of problems happen. Okay, so there's a famous example. The horse raced by the barn fell. Okay, So when you hear the horse raced by the barn, you think that's a complete sentence. Then suddenly there's a verb at the end, fell. So I'm talking about the horse that was racing by the barn, fell down. Okay? So just the appearance of that last word forces your linguistic cognitive process to reprocess what I was talking about. Okay? And so there's a lot of these types of sentences that show this constituency as building up mentally in your representation. And it's only finalized when you hear the entire sentence. Okay? Sometimes it's over multiple sentences, not just a single sentence. Okay? So, Stephanie is talking about recursive here. Do you have another slide about context-free grammar and things of that sort?
No.
No, okay. So I want to go over that a little bit. Does everyone know who Noam Chomsky is? Yeah. So he's not just a linguist, by the way. He's actually more famous for something else.
Yes.
For being a politician, right? He's a big political critic, very much on the conservative side of things. Okay, so he's much more well known for that. But in linguistics, he's a huge star because he came up with this idea of the taxonomy of languages. Okay, and this idea of universal grammar. So if you haven't heard about universal grammar, I'll give you the 2-minute tutorial about it. Okay, basically, what in universal grammar, his theory is that human beings cannot manifest any type of language. That we are born innate with the capacity to learn certain types of languages. Okay? And these languages have some type of switch. Okay? Like you can either put adjectives in front of nouns or you can put them behind nouns. Okay? It seems like there's only 2 places to put them, but that's not true. You can scatter them wherever you want in the sense. Okay? So Chomsky theorizes that in universal grammar, there are a number of these switches that can be turned on or off to realize different languages. Okay? If you're born in a Chinese language family, you speak Chinese, certain parameters of those checkboxes are turned on and some of them are not. Okay? And if you were born into an American household, you learn English, American English, certain of those checks are set another way, and certain of them are not. So for example, English and Chinese both have modifiers normally in the front, right? But Spanish has them in the back, Japanese has them in the back, for example. Okay? So not all of the 3 parameters about how you can throw word salad around actually exist in human language. It's a bias. There's certain structures that are more common than others. Okay? So for example, English is subject, verb, object. Right? Japanese is subject, object, verb, or object, subject, verb, but verb are always final. Okay? So these types of structures are set by universal grammar. Okay? Not everywhere you can scatter everything. Okay? And that's the tutorial about universal grammar. It's a great cocktail thing to know. So if you ever run into a linguist or someone from FASF, you can debate about that. Okay? But the other thing I want to tell you about is about context-free and context-sensitive grammar. Okay? So what's a context-free grammar? Go ahead.
It's a 7 tuple with states, actions.
Okay, you got it from the Wikipedia page.
No, we are saying theory of combination.
Oh, okay, yeah. So you know all about the context-free, right? Context-free grammar is basically the idea that you have a set of production rules, right? And on the left-hand side of the production rule, you have a number of non-terminals. You see those non-terminals exactly as they are. You're allowed to use the right side of the rule to generate another thing. So I can say A and A, B as a sequence can be replaced by going to the right-hand side, C, D, E. Okay? That means wherever I see A, B, regardless of the context, I can replace it with C, D, E. Okay? All right. Now, there are also things like context-sensitive grammar. Okay? And that's actually, I think the one that I gave an example of more context-sensitive. Okay, context free means I have a single non-terminal on the left. Okay, when I have something like, imagine two rules, okay? L, A, R can be substituted as X, okay? And L, I don't know, L, A, Y can be substituted as Z, okay? Then the only difference here is the context on the left-hand side. I am trying to replace A, the middle character, with something else, but it's dependent on the context. What letter, like L is on the left, what letter is L on the right. Okay? That's a context-sensitive rule. It means that whatever I'm trying to replace depends on the context. Okay, so I'll write it up for you. So let's say I have a non-terminal A. Okay, I have L1, L2, R1, R2, and I say I can replace this one with, I don't know, B, and L2 I can replace it with C. Okay, you see what I wrote? It's really faint. I'm sorry about that. Okay, what does it say? Just focus on the middle letter here. This is an A, right? What is the A doing? It's transforming to another letter. Okay, but only in certain contexts, right? This one says you can change an A to a B only when you see L1 on the left and R1 on the right. Okay, and then you can only transform A to C when you have L2 on the left, R2 on the right. Okay, contrast that with a rule like this. All right, what does this rule say? I can replace A with B. Where? I don't care. You can do it anywhere you want. Right? So this is what is called context-free rule, right? Because it doesn't rely on a specific context where you can replace it. Okay? And what Chomsky developed through his intuition of language is a hierarchy of languages. You see that context-free languages are somehow much more impoverished in their representational power compared to context-sensitive. Because I cannot write a rule in a context-free language that corresponds to something like that. Okay? If I only have one non-terminal on the left, I can never write rules like this that only allow me to change A in a certain context. Okay? So there is this hierarchy of language that Chomsky created that you guys should know about. It's very important for parsing. Okay? Because when we parse, if we have a more basic, primitive version of language, it's a lot faster to parse. There are less combinations that are admissible. Okay? So we want to use simpler languages to get away with things, and only use more complicated languages because, you know, there's an exponential explosion in possibilities when necessary. Okay? So we actually know that natural language is not context-free. Okay? There are lots of cases in which that's the problem. You can look this up yourself. What is it? When there's inversion or crossing dependencies, for example, in French and other languages, some words, they branch, and there's two parts of the construction, like in a path, that sit on either side, and there's something in the middle, okay, that won't be able to be constructed by context-free grammar. Okay? So hopefully that gives you some intuition about why this is important, okay? The important thing here is the context-free is less expensive. Many parsers just understand this. Some things that you do on the command line are context-free, so if you use a regular expression, congratulations, you know a context-free grammar. Okay? All right.
So, to continue on, so what are the arguments for why Chomsky thinks that recursion language can be recursive, and it should be a natural way for describing the language. The first is that it helps disambiguation, because you can break down and also start to combine them and compose sentences from the noun phrases, prepositional phrase, verb phrase, etc., which we talked about earlier. And the second point is to help for tasks with specific phrases. And I think Bob mentioned just now that it also works better for some tasks where we use a tree structure, because there will be lesser computational costs. So maybe earlier on in the first few lectures, mentioned about word vector, the idea of word vectors. So in the context of constituency parsing, the question we would consider is how can we represent the meaning of longer phrases? The thing is that perhaps we would like to map them into the same vector space as the word vector space. And how can we do that? So I will just answer that question. How should we map phrases into a vector space? Then we can consider this principle, which is the principle of compositionality, which is that the meaning of a sentence is determined by the meaning of its words and also the rules that combine it. And by combining the word vector, perhaps we can compute a new phrase vector. Same here for of my birth. We can compose a phrase vector for my birth, and then of my birth, and then finally overall phrase vector for the country of my birth. And then we attempt to try to map this phrase vector into the existing vector space.
So this is an important point. So I want you to relate what we just talked about, the lexicon and the grammar. Okay. So what's the lexicon here? There are word embeddings. Do you remember word embedding? The idea of a word embedding is basically you map a one-hot vector of a single word, right? And you use the distributional contextual information of a large corpus. Right? You try to train a lower dimensional vector, so we 50 to 300 dimensions, right, to represent that context. And those 300 or 50 dimensions are randomly initialized and then optimized in such a way that each of those dimensions carries some significance. Right? Not reducible to any specific semantic component, but basically jointly they represent that word and how similar these are. So that's what lexicon now is, our word embedding. Previously, it's just a lookup table to say what word has what type. What's our grammar now? What's the grammar? What's the grammar doing? Yeah, we're combining vectors together that are in the production rule, that we wrote some production rules before, like S sentence goes to V2, N2 plus VB. So the production rule specifies what rows things have. Like the NP is the first argument, VP is the second argument. But because they have different logical components, we might treat them differently. right? So for example, in a noun phrase, like the red car, okay, 3 words. How would we define the structure? How would we define what that is? Would we take the average of all 3 of the embeddings? No, right? Why would we want to use the structure from the phrase structure grammar or the context free grammar to help inform us? Is the red car a type of the? Is the red car a type of red? Is the red car a type of car? Right? So we know that car somehow is the head of the noun phrase. It represents what type of category it is. What type of car is it? It's a red car, right? So red modifies car. That's why we have a structure like my verb, right? And then on top of that, I know that my verb is being prepositionalized into a prepositional phrase. So all this modifying my verb. It's the head of that category. Okay? The red car is still the head. Does modifying red car, and red is modifying car, right? So we're using these types of structure rules, these phrase structure grammars or production rules, to learn what type of part of the embedding to pay attention to. Okay, you can think of it in that attention guise if you like, all right? Meaning that I want to do some type of composition between the words in the production rule, but I want to be sensitive to which words are more important and what role they play. Okay? So you can think about, maybe I involve the two words together, I can average them, I can take max pull, or I put more weight on the head of the phrase versus the modifier of the phrase. All those things are possible. But the important thing is, exactly like what Stephanie has on this slide at the bottom corner, is that the models that we have, because they come from a production rule, they not only specify what the semantics of the phrase is, but how we got it. Okay? What's the derivation of this embedding? Okay, this vectorized representation. Okay? So you can see from the diagram there, right, the country of my birth, the place where I was born, those are close to each other. They also happen in this example that Richard made up, be close to Germany and France. Right? So those are country names anyway. Right? So that's the idea behind that.
Okay, so now I'd like to talk about what are the goals of constituency sentence parsing. Now that we have thought about how to map the phrases into the existing word vector space. So in constituency sentence parsing, what we actually want is to, from the syntactic phrase structure of the tree, we would like to build a semantic representation. And so we first learn the syntactic phrase structure of the tree, and then we calculate the semantics of the groupings, or what we know as the constituents. So for example, the cat forms an NP, the noun phrase, for which we will calculate the vector for the noun phrase, and that's a semantic. And we do likewise for the mat, and we get 3, 3. And then we go upwards to the tree until we form the sentence again. So these are the new semantic representations that are circled in this brown color. And we also have the syntactic structure, which is the tree structure itself. So that would be important for us in understanding how this semantic representation can be understood. Now that we learn how to compute at every level of the tree, starting from the bottom. So it's a bottom-up approach. Actually, that's all I have. So using your master. Yes. Okay, that part Eugene will cover because there is a scoring aspect. I'm giving the introduction, which is great that you asked. He will answer your question about that.
Okay, I was just scrolling. How do I full screen this? Oh, sure. Okay. In the meantime, just a short break from NLP. Since I just finished my theory of computation midterms, I just want to show you something about CFG. So we talked about language just now. So it turns out that this language is CFG because you can create a simple production product, right? So S to A S B, or go to nothing, right? So it's for fun. You can try to prove this, that this thing is not CFG. Actually, we call it CFG, context-free language. Yeah, interesting little fun fact. Okay, all right, so. Yeah. Okay, so basically I will just really use their slides. I also don't know much about this, so you can prefix everything of what I'm going to say as I believe, and then if you want to correct me, just do it, okay? So as actually discussed just now, right, there's this two spectrum of how NLP is done throughout the past few years, right? So there's this group of linguists that maps out everything in the tree structures and stuff like that, right? So this is very sophisticated, a lot of rules to it. But then in the NLP scene, people just sort of put everything into a bag of words and shake it out and then just use those to predict stuff, right? So it seems kind of like there's a spectrum between them. So maybe this is why we need to introduce some kind of a new architecture that could probably help to exploit this kind of structures more, right? So these are stuff that she discussed just now. Right, so this is where I probably start. Okay. All right, so the main goal that we want is to exploit the kind of a semantic structure that we have by building the kind of a tree up there, right? So we need okay, so in the classical recurrent neural net style, we have this kind of rules. We just do it word by word throughout the whole sentence and then come up with a vector at the end, right? So in the new style, we sort of want to combine vectors together. So there are a few questions we have to ask, like how do we combine the vectors, right? And which vectors to combine, right? So we need to take care of those things. Okay, so one way to do this is through something called the tree recursive neural net. Okay, so what they do is first, you take two vectors, go through a neural net, and output two things. first is the proposed new vector, and second is the score about how plausible the new node is. Okay, so in the grand scheme of things, I'll show. So in the grand scheme of things, it goes something like that, right? So you have all the vectors, you propose a new vector, and then you have a score about how good that vector is, and then you do it for all pairs, and then after that you get the max. That will be what you combine. Okay, so that score will tells you which of these candidates should you combine together. Okay. So how do you calculate those new vectors and score? Right? So for the vector, it's just a simple weight times this. Okay, so you concat the two vectors together, and then you just multiply by the weight. So the weight has been trained. That's the part. Okay, yeah. Okay, right. Sorry.
In general sense, how does a recursive neural network
Okay, right. So if you go back to this slide, you can actually see that the things that we've seen before, it's usually just taking word by word, right? So there's a very linear structure to it, right? So in true recursive neural net, we have to decide, in some sense, we have to make the neural net train to know what kind of words we combine together. So it tries to learn the semantic rules of the language itself. Does that make sense?
So it's something especially designed to fit the
Yeah. Yeah. Okay. Right. So so the way that we compute this, as we said just now, is to train some weight vectors, right? Such that if we multiply these weight vectors with a concatenation of these two vectors together, and then we feed it through an activation, we should be able to produce a new vector, right? So this is a new candidate vector. And then you, for the score, what you do is simply just look at all possible. Okay, actually, you know what? Before we go to the score, okay, so I just have to elaborate again. So after you have this, right, you look at the one with the highest score, and then you merge them. Okay, and then now it will generate another new vector, and then you look at the highest score again, you merge them, and then you merge them again and again until you get a tree like that. Okay, dot dot dot. Okay, so now the other question is how do we decide the score? So if you can look at this, right? This Sn, or where is it? This Sn is actually just compute by a vector multiplication with this P. Okay, so if your P is 2-dimensional in this case, this U is actually also a 2-dimensional vector. Okay, so there's another weight that you have to train. Okay, so if you take a dot product between U and P, you get your score. Okay, right.
So I just want to mention this is quite primitive
Sorry? No.
So,
What's up?
this is very close to everyone with
Mm. Mm.
in terms of your
I see. Okay. So is it repetitive?
No.
Okay. Cool. Right. Okay.
So if you go in traditional language, natural language processing, and you look at chart parsing, this is very similar to the idea of doing that. So the idea is that you start with a lot of these words as a part of speech at the bottom here, and you run dynamic programming to try to compose words that are next to each other into a constituent. Right? So we're using the phrase structure that was up there to pull together separate units that are already constituents, because basically we're using the lexicon to map the constituents, but now we're using neural network to do that. Right? The neural network is, as Eugene already said, proposing a representation of what that phrase is, and then how good a phrase is it. Okay? So we don't actually have production rules anymore, okay? Because we're asking every subsequence of words to come up with a vector representation. Okay? Why is it different? Because, for example, can you give me a subsequence of words that is not a constituent? Okay? Let us do something very simple. The red car. Okay? That's a noun phrase. Can you tell me a sequence of words from there that's not a constituent? Huh? They have to be a subsequence, though. Okay? So there's one subsequence there that's not a good phrase, a good constituent. The red, right? So red doesn't represent anything, right? But we can make, neural networks are good at making things where things don't exist, right? So we can propose what the red looks like as a vector, right? It's a semantic vector. But we also want to output that score on the left, right? The left is score, that 1 point, whatever it is, I can't see. But basically that is telling us how likely that looks like the phrase that we would agree has a semantic category. Okay? So on this chart here, right, we're basically taking all the size 2 things, a little bit like agglomerative clustering, like Mohit was saying, right? Pulling those up to a second level and saying, okay, well, let's pretend we have 2 units next to each other. Which of those 2 units look like they could be actually something bigger than a unit by themselves, right? 2 units put together. So it looks like the cat is not bad because the score, the left-hand side score, looks pretty high. Right? I've seen a lot of those types of structures before. The cat seems to cohere the phrase a lot in other contexts, so I'm going to call it a high score. Right? Lower scores are like cat-sat. Well, cat-sat I see once in a while, but it doesn't seem to be that often occurring, so I'm not going to call it much weight as a constituent. Right? So the idea is to learn these phrase structure rules from data, rather than having somebody sit down and, like a primary school teacher would tell you and say, you have to have this in front of that, you can't modify it this way, all those things that you never really learned, because you learned it from data, right? You never learned how to speak English from a textbook unless you were an L2 learner, meaning a second language learner. Okay, then you have no choice. You have to learn what you learned from another language like Chinese and transfer it using grammar to learn how to speak English. Right? But most of us, babies, they don't pick up a grammar book, memorize it, and then speak fluent English. Right? We all have stories of when we were saying funny things in our parents' class because it was, understandable why you would say that, but not syntactically correct whatever your first language was. Okay? And that's because we observe from data, we're generalizing from data, and we get the nuances wrong, our phrase structure isn't quite right.
Okay, so with that, we now have to define another score, all right? So just now we talked about the score of combining 2 vectors together. Now we have to talk about the score of the current state of the tree, right? So, well, if you look at any particular instance of it, you can actually see that there will be nodes, right? There will be like this nodes here, this nodes here, this nodes here, right? At this stage, there's like this 4 nodes here, right? So what you do is you sum out all the scores of those nodes, right? That will give you the kind of the score of the current tree at any given point in time, okay? So, as we say here, right, the score is actually a function of the sentence and the current state of the path tree. Okay. So then now we can define kind of the loss function that you can train on. Okay. So okay, let's see if I can break down this loss function. So what you do is imagine you have an oracle that tells you, okay, what is the best possible, what's the best possible split of those 3 is. Okay. So this oracle will tell you this thing right here. Okay? And then what you want to do is you want to train such as a loss function will give you whatever the current parse tree and the sentence is, deferred from the oracle version of the cause of the tree itself, the score of the tree itself. Okay? So one thing, of course, in this loss function is how do we get this oracle, right? This doesn't make any sense. So one thing that they did is actually they just do a greedy search through some of the possible trees. So the greedy search part is actually exactly this part, right? So they just take all these things, choose the best, combine, right? So this is the greedy approach of things. Sorry? Yes, I believe so. Mm. Mm. Yeah, it's okay. I'm not super sure about it too, so if anyone has the idea.
I mean, I can probably probably
Yeah,
I
okay.
think it's worth knowing exactly when this is being made for training.
I suppose it makes sense to make this during training, right? It is training? Yeah, okay. This? 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 Oh. Yeah, okay. As I said, the oracle, it doesn't really make any sense because it's the oracle. That is why what they did is they actually just used a greedy approach instead of doing oracle. So I don't know if I'm right, but I sort of think about this as a kind of a bootstrap way. In a sense, have you learned EM before? Sort of like you start with some gas and then you slowly improve your gas using your gas.
You start with a guess, and then you essentially like ask how incoherent is this gas, and then you move in the direction of maximizing coherence.
Mm.
That's
Mm. So does that make sense in this context? Sort of.
So beam search is like something that's a bit like Monte Carlo research.
Mm-hmm.
So I imagine what they're trying to do is that they'll start with a tree all the way at the bottom, and then they'll do some number of random parses of the tree to some depth, and they'll choose the best one. Beam search is so the way beam search works is that it's greedy, but it's greedy, I believe, in a way that like if you go up some levels to the parse, right, and then you get a score, and that score is less than at a lower level of the parse, then you'll go down that you'll go build the lower level tree.
Mm.
You can think of it as tree search, essentially. Roughly.
Okay, so I'll add to that. So what the last bullet here is saying is that we can do a very greedy algorithm and search for the optimal way to pull things together given the current level of the tree. Right? So at a particular level of the tree, when we're making a decision, like on the build-up slides you saw in the animation, right? We're selecting the two nodes that have the best score for combination, and we're pulling them together, right? And then we take in the next iteration, we take the two best nodes that have the highest fitness score for making a new constituent, and we pull them together. Okay, this is a greedy process, right? Because every time we pull together a node, we are constructing a new node in the tree, and we don't have the constituents that it was constructed for anymore. Okay? So for example, if I have the red car, if I take red and car and pull them together, then I only have the and red car to work with. Okay, I don't have the pieces of red car to work with anymore. So I've already combined them together greedily. Okay? So what they're saying is, just like Mohit said last time, is that if you look for all the possible trees, it's super exponential. Right? There are too many ways to combine it. So no one does search in that space. It's just too expensive. So what you have to do is some other structured way of doing it. So beam search is one way of doing it. It says instead of keeping one best thing, okay, the one best structure, I allow myself to keep n best structures. Okay, n best structures at a time. Okay, so I will keep the best structure, but I'll also consider, okay, if I could put two other nodes together, what would those two other nodes be? So let's pretend we have, let's say, n nodes, right? And I need to pull together two of them to form a constituent, right? So I can go through all of these nodes and then select the pair that's the best. But if I want to do beam search, it says, well, I'm not so sure that I'm going to get exactly the right answer at the end of all the steps. So I'm going to say, let's pick 5. Okay? So I picked the 5 best things to pull together, and I'm going to combine all of those in separate experiments, parallel universes. Okay? And then I take those 5 and I do it again, right? So out of the space of 5 things that I've chosen as the best constituents to pull from all of those, I'm going to search all of those 5 for what's the best next step to pull. Okay? So some of those steps could be reproducing things that I just did from the last one, or it could be building on the result that I've just built. Right? So for example, if I combine red car together, then putting the with red car seems like a good idea. Right? But I'm not married to that suggestion because I did a beam search. Right? Which means that I could say, actually after combining these two together, there's nothing nice to combine with afterwards. Right? So I'm going to go back down and look at a different way of searching. Okay? So the idea is very similar to what we do in like A-star search or other algorithms that you might see in game playing, right? So when we do game playing, we'll say in our head, okay, if I make this move, then what else can I do? So instead of making just the best local maximally good move that's best for our loss function, right? I keep a beam. I keep 5 different states that I could suggest, okay, as the possible next move, and then I project forward from those 5 possible states. What are the 5 next possible states that I can be in, right? So what's the move after that? Not just the first move that I can make, but thinking farther down the line. If my opponent moves, then I move again. What are the 5 best states after looking 2 spaces ahead? Okay, so that's what beam search does, right? It says I keep a limited amount of memory. Okay, that's my beam size, and I use that to investigate possibilities. Okay? And in fact, lots of game playing algorithms, if you do, AlphaGo, A-star search type of stuff, we usually tune the beam size to the size of main memory. That makes a lot of sense, right? Or the size of the page of memory that you have in your RAM, right? Because if you run out of memory that's local to your CPU and you have to go out to disk for it, it's going to take forever, right? So you keep the size of your beam consistent with the size of the architecture that you have in your RAM. Your local cache or your RAM size. Heaven forbid you have to go out to disk to get it.
don't do that, right? So that's the idea of being search. Okay? So all of this type of idea, that you don't want to make a greedy step, because later on you might find out, oh, if I move the queen this way and then capture that pawn, it was a good idea, but later on I'm going to suffer for it, right? So I want to make something that's globally coherent over several time steps. Okay, that's the idea of being search. Okay, what that last part there that says with chart, that's the chart parsing algorithm that we talked about before. It's this idea of having the previous constituents built up through the neural network by using those scores, right? The scores on the left-hand side that are red or green, right? So we use that as an indicator of how good the previous constituents that we proposed were, if we want to use that as a basis for doing merging subsequently.
Okay. I'm going to skip this part. I actually do want to discuss this part, because this feels like just math, just like deriving the same thing again and again. Okay, so rather than going through this, I'm going to go through some of the improvements that they made to this tree recursive structure. Okay, so just now what we have did is sort of just combine different word vectors together, independent of what kind of word they are, right? So no matter, we treat noun, and we treat verbs, and we treat adverbs, adjectives, all the same, right? Sorry? Okay, yeah, so maybe I will draw a diagram. Oh, okay, it's just here, right? So what we have here is, this is the previous kind of architecture, right? So we just combine two vectors together, no matter what they are, right? Even if this is a noun and a pronoun, or if this is a verb or a verb, it doesn't really matter, right? Just combine them, doesn't treat them separately, right? So the idea is that if we could actually use this information of what kind of part of speech they are, then that might be better, right? Because if you look at the previous one, we only have one word vector, then we combine these two together, and then we feed this through the same thing, right? So why not we have a different word vector for different pairs of part of speech, right? Maybe one word vector, the weights, right? Why don't we have a different weights for different kind of pair of part of speech? So we could have a weight that is specially catered to, say, a verb and a noun, right? And then maybe another one for a noun and a noun, okay? Or maybe one with pronoun then a verb or something like that, right? Maybe that will improve the results, okay? So this is what they mean by this syntactically syntactically recursive neural net, right? So the idea is just to train more weights, okay? Each of different pair of the kind of a part of speech. Okay, so one thing maybe we would like to discuss is, so do you think that this is actually going to give a better results? Yeah, so why?
Specialize. I mean, it's sort of like whatever you explain just now sort of makes sense. So therefore, better results.
Okay. Okay. Maybe let me rephrase the question a bit. Like, the problem with this is that now you have less training sample for each pair, isn't it? Like for this one, every pair is part of the training sample. that sometimes you have very rare pairs of words, right? So would that affect the result? I don't know the answer, but anyone have any comments about that?
Well, the deep learning answer is very, optimistic. It's like, oh, the data people don't worry about how much
Train it over Wikipedia or something.
the monkeys to handle it.
Oh, right. I mean, yeah, that's kind of true. The Wikipedia. Okay. But anyway, okay, never mind. I do have one more. Okay, here. This is one more extension to it. Okay. Let's see. Okay, so one other problem with the current architecture that we have is that it always looks at this pair of words by multiplying this weight vector, this weight matrix with your word vectors, right? And it kind of feels like this, right? Imagine if you had your weight. It's just basically doing an addition, right? It's just doing an addition of two dot products, right? So the problem with this is that it seems like this weight matrix is trained separately from this weight matrix, right? There's sort of no link between these two, right? So it would be great if we can intertwine these two words together in some sense, right? So, so what they did is basically to introduce, instead of just a word vector, we have a word matrix, right? So each of the words is represented by a vector and a matrix, okay? So just extend the idea from word vector to matrix. Right? So now we have a pair to describe each word. Right? So Barry has a vector and a matrix. Good has a vector and a matrix. Moody has a vector and a matrix. So now let's just redefine how we combine things together. Right? So similar to the previous thing, what we do now is instead of just taking the weights and then multiplying with your word vectors, you take this vector and you multiply with this matrix, and you take this matrix and multiply by this vector. So in terms you get two vectors, right? This is a matrix times a vector, which gives you a vector, a matrix times a vector, you get a vector, and now you combine those two vectors together, right? So this, you combine those two vectors together and do the classic way of just multiplying by a weight. Okay? So you sort of get a new set of vectors here. Okay? But the problem with this is that it needs to go down the tree all the way, right? It needs to go out the tree, and now we only have a vector. So we need to produce a matrix for that too. Okay? So how do we do that? Very simple. We just train another weights, right? Just train another weights to multiply that with this, right? So what you do is you concatenate this into a 2n by n matrix, and then you just multiply by some weight. Okay, so anytime you need things, you just multiply by weights and let the deep learning stuff do its work, right?
Okay, so it seems like now W, so is there one W now, or is there multiple?
Okay, maybe let me draw a diagram to illustrate this. So we start off with words. Let's say you have a little cat, right? So each of these words is represented by, say, a vector and a matrix. Okay, a vector and a matrix. A vector and a matrix. Okay. So now, if you want to combine these two together, what we'll do is simply just take this vector. Let's call this vector WA, and this. Oh, okay. Let's call this vector A, then A, B, and B, right? So the first stage is to combine this together, and you get something like AB plus BA, which is going to be R2, right? It's going to be a vector, right? Then after that, what you do is this is the new representation of a little. Okay. Now, the problem with just having this representation is that it's not able to combine later on, because we need each representation to be a pair of vector and matrix. So, in this particular case, we have one weight to get this. Okay, let's call this weight 1. Then we need another weight here to get this representation here. And to get this representation, what we do is we just take A and B, we concatenate together. This is just A and B, we concatenate A and B together, and we multiply by another weight here. So this is this, and this is this. Make sense?
So, Well, I mean, I see moving out, like, just
I guess the iteration is just you want to intertwine things together, and the best way to do it is just introduce that.
I mean, like, if you just throw stuff together.
Yeah, I guess
Is
it's,
intertwining in a good way? Is it?
yeah, I probably can't answer that. Anyone wants to answer that?
Okay, so the reason why you have two different representations here is that you think of certain words as modifying other words. Okay, so when you have a modification, you can think of it as like a convolution operation or some nonlinear function. It's a function that takes inputs and translates it into another state. Okay, so for example, the word vary. What does it do? It's intensifying the word. Does it have a semantic meaning of its own, like car? No, right? It's an intensifier. It does some type of transformation on an object. Okay, so that's why they say you want matrix. Basically, some type of operation on vectors. Okay, that can compute another vector. As the representation of certain words, like there. Okay? Now there are other words, like car. Okay? Car is not an operator. You can't car things. Okay? You can vary things. You can jump things. You can fill in things. Okay? But because it's not an operator, you would say it has specific semantics. Okay? That is a vector form. Okay? So when we take a vector, we compose it with an operation, we get out another vector. So we can say a very long car is sometimes a car, which is very long. It's been intensified. Okay? On the other hand, there are certain other things that we would say are not like that, right? So if I take, I don't know, mail and box, or tele and vision, and I stick those two words together, somehow they're the combination of those two words. So the normal idea of composing two vectors together makes sense. Okay? So what this paper was trying to do is say there are two really different types of operations happening in language. There's the idea that things, when grouped together, like A plus B is some type of A and B thing, right? And there's another type of thing when you take A plus B, it's A is a function that operates on B, or B is a function that operates on A. Does that make sense? So that's why they want both a vector representation, which is more like the noun version of something, if you will, okay, it carries the semantics, and then matrix version, which is an operation version, the transformation operation, F, a nonlinear function, if you will, that is doing some translation, okay, doing some type of operation to say something else. Like, for example, in the, I don't know, embedding literature, you see all these things like, is the capital of, you know, and then you see a translation of a vector like, I don't know, Washington, D.C. goes to USA, right? So that arrow is basically trying to be computed through this matrix operation. Does that make sense? Okay. So that's what this paper is trying to do, is to say that because I don't know which thing it's doing, right? So I have vary and good. I don't know whether vary is supposed to modify good or good is supposed to modify vary. Let's just do the stupidest thing and try both. Okay, which is what they are proposing, right? They say, if I have a vector and a matrix form of everything, then I take the vector and multiply the vector from one side and then multiply it with the matrix on the other side. Or I take the matrix on one side and multiply it with a vector on the other side. And I'm going to get out a corresponding matrix or a corresponding vector, right? So then I'm saying something like very good is some composite. Right? It could either be an operator, and otherwise, what that means is that very good is itself some type of transformation, right? In which we would believe that the matrix form of that operation is what is valid, right? Or we could say that very good is some type of vector, right, is some type of unit that has some semantics, right? So you can see the difference. If I put very good together, right, I should get out an operator because very good itself is a modifier that can modify other things, right? But if I put red car together, it's the same type of thing, right? Because I have a modifier plus something else. I compose them together, but I would want red car to be something that looks like a noun, right? Not an operator. It's a, you know, an object. Okay. So what they're doing in this work is saying, I don't know which one it is. We'll just let the math figure it out. Okay. You just at every time you combine things, admit both a vector and admit a matrix. Right? The vector is the noun version. The matrix is the operator version. Okay. Does that give you the intuition? Okay.
I also want to mention the thing is that this has to be done because when you look at syntactic and type arguments,
Previous
yeah,
slide.
yeah. So like remember I brought up, well, here you're saying, oh, why don't we just get more data for all time? Well, it might be that there's not enough data. Yeah, it might be that there's not enough elements, valid elements in the unit itself. And then you're saying that this is impossible. But if you try to do it for every single combination, you'll see that money is actually impossible. So it's not a question. No matter how much data you get from the universe itself is not enough. So that's why I was
So this particular structure is basically just saying that we can use our prior knowledge about syntactic categories to inform the selection of weights, right? So we believe when we combine a noun phrase with a verb phrase, that something very different is happening than when we combine an adjective with a noun, right? So the specialization that you see on that slide is that just that one location in the upper right-hand corner of the right side is just to say that I'm going to change the weight matrix, right? We want that specific to the parts of speech that are involved, right? And yeah, you could say, okay, well that sounds like a bad idea because I have sparse data, but it's not true because in most languages we have very few parts of speech. Okay? So it's not true of word identity. Right? We have an unlimited amount of nouns, unlimited amount of verbs. In fact, we make verbs and nouns up every day. Okay? But that's not true of parts of speech. There are only a controlled number of parts of speech. Okay? Since what you see in the weight matrix index, right, is basically a part of speech. That P there is a part of speech. Okay, so it's basically saying I'm blowing up the weight matrix by a constant linear factor, but a constant factor, okay, because there are only a certain number of parts of speech. Okay, in English, maybe about 20. Okay. So instead of having 1 W, I have 20 W's, that means 20 more times data. But if I have a lot of data to start out with, that 20 is not a very big deal. So you can put both of these things together. Okay, so the version 3 that Eugene is proposing here is basically without the notion of syntactic category at all. Right? It's just saying we think there are things that are operators, we think there are things that are operands, okay, and we just go learn them without appeal to any linguistic knowledge whatsoever. Version 2 that was presented before says, I actually know what part of speech things are, and I want to inject that as a regularizing component into my neural network. Okay? But parts of speech are, I mean, most of us would agree what is a noun, what is a verb, right? So why do you have to go learn those things? Why don't we just go ahead and specialize it, inject our knowledge, and make it easier for us? Okay.
Yep. I guess I only have one last thing to say. So one thing that they did is actually they tried to extend this idea of tree recursive to image segmentation. Right. So that's one thing. Oh yeah, and one more thing to say, right? At the start of this lecture, I remember the prof actually said something about it's kind of a area of NLP that not a lot of people use, right? It's relatively new, very little papers on it and stuff like that. So actually, I do not know how feasible all these techniques are. Yeah. So that's one thing.
So all these, I think architectures are a little bit more sophisticated because they introduce structure and they're trying to put in more constraints. And what you've seen from deep learning is you get better gains from feeding more data than having more structure. Okay, so that has always been the win over the last couple of years. Is, you make simple use of resources that you can use at scale. Right? And that seems to make bigger wins than other things. Okay. Even in the computer vision area, they've been trying to use more informed features, but actually they find that just trying to structure the deep learning problems in such a way that they can take advantage of the architecture of the components, like what the structure of the GPUs are, what type of constraints they are, that has a better effect in learning than using structure. Okay. So what it means for us is that we are at a stage where there's still a lot of very low-hanging fruit to be gathered. Okay? Because all of these structural things that we're talking about, they are actually very important to modeling. Very, very important. The problem is, stupid things done at scale still work better than introducing more knowledge. Okay? That will run out. It will run out. And when it does, people who have thought about structure or have read about it will be continually able to make gains. Because all the low-hanging fruit have been tucked away. Right? But right now, because there's still so much more room to push in more data, to use attention or even other things that are very easy to get gains on, you can make plenty of progress that way. Okay?
I have nothing to add on.
Okay, so let's thank our presenters.
Okay. I want to spend 1 or 2 minutes making sure we're all together with respect to our class. Okay, and then we'll go. We can finish a little early. Not early anyways. Okay. Okay, we are here at Tree Recursive Networks. We still have advanced architectures in week 11. Who here is in week 11? Okay, you guys please come and meet with your questionnaires. I think there's some questionnaires in the room too. Okay, and then we have week 12 and week 13. Anyone here from week 12? Only one person? Okay, so you can go check on Slack and try to pull them down to make sure that we get started on that. Who is here for week 13? Okay, at least 2 of us. Okay, great. So we do want to make sure we have enough presenters and questionnaires for these. Okay, otherwise I will just talk more. Okay, so yeah, I hope we have enough people to try to present the slides. Okay. The other thing we need to do is, you know, some of you still haven't put the project abstracts on the 61. Sorry, on the STEPS site. So please go to STEPS. Okay. Log in. Okay. Then you can go to your settings to manage the events. I think you should all have gotten a an email to log in, and then you would just do like what I did. Go to Manage Events, okay, and then select the module 6101, and then you just need to modify this. So I can see many of you haven't put in things yet. So please put them in so that we can have some representative information. Those of you who put them in, thank you very much for doing that. And we hope that you're getting along with your projects. If you have any questions about your projects that I could possibly help you with, I will try my best. But of course, I'm only one person. I don't know that much of all the things that you're doing. So you're welcome to consult me, and I'll try to help. Okay? Any questions? No? Okay, thank you very much. I'll stick around if you guys have questions. Otherwise, we'll see you next week for week 11. Okay.